y equals the inverse tan of x. We're asked to, assuming the derivative of tan x, to find the derivative, essentially. Show that it's 1 over 1 plus x squared. And the way we do this is a little bit of a hint, is to make x the subject. So x equals tan y. By the way, you would do this also for inverse sine, inverse cos, and even something like ln x. For ln x, you'd make it x equals e to the y, and then differentiate that and go from here. But anyway, back to this one. We now find dx by dy. And this is given in the formula, but the derivative of tan y is sec squared. You can use the quotient rule to show it, but we can just use the formula book here. And that means dy by dx equals 1 over sec squared y. Really good. We just want to get it back in terms of x, which we don't have at the moment. So let's seek to find a relationship between tan y and sec squared. Okay, well, there is sine squared plus cos squared is identical to 1. And remember, there's two other identities that come from this. One of them we divide through by cos squared, which gives us tan squared, plus 1 is identical to sec squared. There we go. That is the one we want. So this becomes 1 over 1 plus tan squared y. Tan y is x, remember? So we're there. We get 1 over 1 plus x squared. That is the derivative of inverse tan. Next up, we're given that f of x is x times the inverse tan of 4x, and we're asked to integrate it. Okay, let's go for it then. So we're going to get, this is part B, we're going to get the integral of x inverse tan 4x dx. Now remember, we've got this result. Surely that's going to come into it somewhere. Well, this is looking like it's going to be by parts. It's not like it'll be a substitution or anything that's going to work. It is a product and it involves x. That's always code for it, really. Now, which one do we let equal u? And which one do we equal v dash? Now, if you have x sine x, you would let u equal, you'd let u equal x. But in this case, if I let u equals x, I'm going to have to integrate inverse tan. And earlier on in the question, they kind of guided us towards differentiating tan. So that seemed to be a bit of a hint. And what we're going to do is set that one equal to u and that one equal to v dash, going against the normal approach you would get with x e to the x, x sine x, and so on. Quite often when I teach A-level maths, I talk about you following this like little rule. You make logs your u, and then you go with algebra, but it kind of falls apart in this sort of situation. You actually make your trig, because it's inverse tan, you make that one equal to u. Otherwise, you get into difficulties because you're going to have to integrate inverse tan, which is itself not particularly nice. So we're not doing that here. I'm actually not sure if it would work. Not sure. Going to carry on with our approach here. Right. So u dash is going to be, now we can differentiate inverse tan of 4x using the chain rule. So I'm going to differentiate the outside as inverse tan of something, but keeping the inside the same. So I'll get 1 plus 4x all squared. And I times by the derivative of the inside, we're going to get 4 on the top. I'll leave it like that for the moment. And then v is the integral of x. I'm going to get half x squared. So then we use our formula. This is in the formula book, uv minus the integral of u dash v. So that will give me a half x squared inverse tan of 4x. All right, we've got that term sorted. And then I'm minusing u dash times v. Okay, well that will become, let me write it out. Don't want to skip too much. 4 over 1 plus 4x squared. Multiplied by a half x squared. And it's this now we've got to contend with. Somehow we're going to be able to integrate it. Okay, just going to focus on this in isolation. Let me label it star. And star will become the integral of 2x squared over 1 plus, for the moment I'm going to expand it, 16x squared dx. Okay, now this might first look like a really challenging integral because it's not like this f dash x, so the f of x, we can't just write it as a ln. It's not partial fractions. Is it really going to be a substitution? And the answer to that, to all of these, is no. And here's how you can deal with it. We're going to try and get it so that the numerator is actually 1 plus 16x squared. And then it will all kind of cancel out to 1. We'll just have an extra bit after, but we'll have dealt with the x squared. So I'm first of all going to times through by 8 and divide by 8. So I can write it as 1 over 8, 16x squared over 1 plus 16x squared. And we're going to use a nice little idea. I'm actually going to add 1 and minus 1. I haven't changed it. But then I can write it as 1 plus 16x squared over 1 plus 16x squared. And then that other bit becomes minus 1 over 1 plus 16x squared, which I'm now going to return to being 4x all squared. Incredible, because this just becomes 1, and now I've turned what a really awkward integral to like the integral of 1, and then something that I know, because this is kind of in the form 1 over 1 plus x squared, albeit there's a 4 in there, but we can use the chain rule to help us. So I will now get 1 over 8, and then it will be, actually, it's not no square brackets because it's an indefinite integral. We're going to get an x minus inverse tan of 4x. Now think about what happened when we differentiated this earlier. Okay, because here it is. When we differentiated inverse tan of 4x, we got 4 times 1 plus 4x all squared. So all I need to do here is have a quarter to kind of balance that out. All right, and that is star. So therefore, the integral of f of x dx is going to be the term that we had at the very beginning, a half x squared inverse tan of 4x. And then I'm going to be minusing this thing here. Well, let's expand the bracket, 1/8 x. And then it's going to be minus, so it's going to become a plus 1 over 32 inverse tan of 4x. Just got to remember the arbitrary constant, which is normally plus c, but they've put a plus k in their answer, so I'll leave it like that. If we just have a little glance up here, yeah, we've shown it. We've got this term. We've got this term. Do we need to, like, we have determined a, b, and c. We don't actually have to state them. You can if you like. Then hence find in exact form the mean value of the function over the integral 0 to root 3 over 4. Okay, let's do it. So just a little sketch. I don't know what this function looks like originally. It's gonna, if we integrated it between 0 and root 3 over 4, we would get this area here. And the mean value is when we then draw a line going across and we create a rectangle with the same area. It's got the same base, and that height is the mean value. So to work it out, we're going to find the area. We're going to integrate this f of x between 0 and root 3 over 4. But then we're going to divide by root 3 over 4 because that is the base, which is the same as times in by 4 over root 3. Now we've just done the integration, so all I've got to do is sub in to this answer up here, a half x squared, etc. Okay, and of course we don't need the arbitrary constant here. Let me just move it because it's kind of impacting on my sketch. All right, perfect. Sub in root 3 over 4, we're going to get a half. times 3 over 16 times inverse tan of root 3. Then minus 1 over 8 times root 3 over 4 plus 1 over 32 inverse tan of root 3. And then we're going to be minusing when we substitute 0 in. But actually, when you substitute 0 in, you get 0. Inverse tan of 0 is 0. And then, yeah, 1/8 times 0 is 0. So I don't need any of them. Just close the bracket. So I'm going to get 3 over 32. And then inverse tan of root 3 is pi over 3. You can use your calculator. You might know that as an exact value. Then minus root 3 over 32 plus 1 over 32 times pi over 3. Amazing. I'm going to continue to tidy this up. So 3 over 32 lots of pi over 3 plus 1 lot over 32 lots of pi over 3 is 4 over 32, or 1 over 8 lots of pi over 3. And then I'll get 4 over root 3 times 1 over 8. That will become 1 over 6 root 3 pi, or pi over 6 root 3. And the other one, the root 3s are going to cancel. I've got 4 over 32. It's going to be 1 over 8. So minus 1 over 8. And that is our mean value. You can, of course, and I would recommend this if you got time, although I think this is quite a time-pressured paper. You could actually put your function in the original function, remember x inverse tan of 4x, work out this integral on your calculator, get a decimal answer, and then just check that it's the same as this one. And it will be. I'm not going to do it here, but that's a little check that just takes half a minute if you're happy to do it. You know, you can be really confident you got it right.